Okay, so continuing with the chapter of stoichiometry, uh, the last thing we discussed was empirical formulas and using empirical formulas to find out the molecular or chemical formula of a certain compound. Now, today we're going to uh, move on and talk about moles and chemical equations. But before we get into that, let's just quickly review the chapter and particularly all the formula that we've come across, because we'll be needing all of them. All right, so if we're familiar with the concept of the mole, it is the amount of substance that has 6.02 into 10 to the power 23 particles of that substance. Normally what we do is we take the relative mass of a substance, whether it's an element or a compound, and we equate that to mass in grams, and that is called the molar mass. And within that molar mass, we it said that it is 1 mole, right? So you would expect to find 6.02 into 10 to the power 23 particles, whether they're atoms or molecules, in 1 molar mass of a substance, right? So some of them over here, and that is called the Avogadro's number, Avogadro's constant. So it doesn't matter whether you have 12 grams of carbon, 44 grams of carbon dioxide, or 100 grams of calcium carbonate, right? Each of these are the molar masses, and each of these have the same number of particles, 1 mole. So we did some calculations, right, about number of particles and moles and mass, and we came to the very first formula that we need to know, and that is number of moles is the mass of an element divided by the molar mass. And you can move this around, obviously. Let me get the highlighter out. Yeah. So you can move this around depending on what it is you have and what you need to find, right? But the basic is number of moles is mass of an element divided by the molar mass. This is, right, that same thing moved about. So the mass of a compound is, right, number of moles multiplied by molar mass, which is, right, what you have here. And, right, so same thing. So there's some questions regarding that. Then we came to talking about gases, and Avogadro's law states that equal volumes of gases at RTP have the same number of particles, or in other terms, 1 mole of a gas at room temperature and pressure. Room, like, pressure is 1 atmosphere, and room temperature is about 25 degrees centigrade. So under those conditions, 1 mole of a gas will occupy the same volume, which is 24 decimeter cubes or 24 liters of volume, and will have obviously 6.02 into 10 to the power 23 particles. The formula to consider is number of moles of gas is volume of gas, so whatever volume we are using, in decimeter cubes. If it's given in centimeter cube, we divide by 1,000. That's a volume of gas divided by 24. And of course, you move that around and you get number of moles. Volume of gas is number of moles multiplied by 24. So some questions using that, right? Then we came to moles and solutions. So if you're dealing with solutions, we're dealing with liquids. And so the concentration of a particular solution in mole per decimeter cube, so how many moles you have in per liter of that solution, can be given by a number of moles divided by the volume that we're using. Right, and so 1 ml is 1 centimeter cube, 1,000 ml is 1 liter, which is 1 centimeter cube, 1,000 centimeter cube, which is written as 1 decimeter cube. And also, if you move this about, number of moles is concentration multiplied by volume of the solution. So some questions relating to that. And every time what we did was convert the given volume into decimeter cube, because that's what we need, right? Volume of decimeter cube. Then we talked about calculating empirical formulae. Now this will not come in handy today, right? It is a separate topic within the mole chapter. But what we know is it's important to have balanced equations and correct chemical formulae, so that we are able to figure out how much of each substance is used. When we went on to calculating empirical formula, so there was a substance which was 92.3% carbon and 7.7%. There's another question back here, wasn't it?
Yeah.
No, it was in the text. I showed it to you from the text. Okay. So 92.3% carbon and 7.7% hydrogen, and it had a relative molecular mass of 78. And you're asked to find the formula for that compound. So the percentage written down, and because it's a percentage, it's out of 100. So assuming we have 100 grams of this substance, 92.3%, 92.3 grams of that substance would be carbon, and 7.7 grams would be hydrogen. The number of moles of each, right, are the same, and that gives, right, so we divide 92.3 by 12 for carbon and 7.7 by 1 for hydrogen. That gives us the number of moles of each. And so the molar ratio for carbon to hydrogen is 1:1, which is interesting, right? What we do is we find the relative mass of the empirical formula. So that's CH, 1:1, and that's 13. And then we divide the molecular mass by the empirical mass, and we get 6. So whatever compound we have is 6 times CH, which gives us C6H6. Now this is not something we've learned. It's not part of the syllabus, but just so you know, it is a molecule called benzene, right? So that's how we go about doing it. Now today, the first thing we're going to learn is when you write a balanced chemical equation, not only do you know the number of moles of reactants and products, you also get to know the masses, and there's an interesting thing as far as the mass is concerned. So the example we're going to use is magnesium burning in oxygen to form magnesium oxide. And to write that out, we've got Mg plus O2 giving us magnesium oxide. This guy is a solid, this one's a gas, and this is solid as well. Sobia, would you like to balance this?
Sure. We have two oxygen on the left side, so we're gonna put 2 on the right side as well.
Okay,
That makes it 2 magnesium, if I'm not wrong.
yes. 2 of
So,
magnesium and 2 of oxygen.
so 2 on the product side for magnesium as well.
The reactant side.
Yeah, sorry, reactant side.
Right, and it's balanced. Right, this tells us that 2 moles of magnesium react with 1 mole of oxygen to give 2 moles of magnesium oxide. And this is how the reaction happens, right? It's not something that we can say, it's not necessary. No, these are the ratios in which the reaction takes place. And that is why it is important for the chemical equation to be balanced. Now, seeing that 2 moles of magnesium are used, right? What's the mass? So what's the molar mass of magnesium? Do you like have a periodic table on hand? Hmm?
Uh, it's for magnesium. It's 24.
Yeah. So you've got the molar mass is 24 and you've got two of that. Oxygen is 16, but you've got, right, molecular oxygen, it's diatomic. So that's 16 times 2. Even though it's 1 mole, but it's 1 mole of oxygen, as in like the gas which is diatomic, right? That's why we're doing 16 times 2. And
Yeah.
then, right, magnesium oxide. So you're getting 24 plus 16, and you got 2 moles of that. And what you get out of this, you have 48 and 32, giving you, what's that? 24 and 16 is 40 times 2 is 80, right?
Yeah.
The interesting thing is, what's 48 plus 32?
Wait, I gotta check that. 80.
80.
Yeah.
And so what we notice is that the mass of reactants is equal to the mass of products. Oops. Right? And in a balanced equation where all the reactants and all the products are taken into account, this is what you would expect to find, right? That the masses are equal on both sides. And this is called the law of conservation of mass, right? Now, the law itself we're not going to detail, but since it's mentioned, it is linked with the law of conservation of energy, which we touched on in physics when we were talking about nuclear fission and fusion. Remember? E equals to mc squared,
Yeah. Yeah.
right? And they mentioned that energy and mass are interchangeable and everything. So energy is conserved, mass is also conserved, right? So you don't just lose mass. If mass is being lost, that means it's going somewhere, right? In many cases, it could be lost as energy in some form, right? But
Yeah.
on paper, at least, right, theoretically, it should be equal. What happens in reality, we'll take a look at percentage yield later on, and we'll see that things don't really go the way we expect them to. Okay.
Yeah.
Okay. Now, this concept can be applied to solids, liquids, and gases. And because we just took a look at the formula used, slightly different, but right, at least the way they've explained it seems pretty straightforward. So, the example they're giving for solids, right, is that of lime. So, lime is manufactured from limestone, right? It is heated and you get something called lime, and carbon dioxide gas is given off. What is limestone? We've come across it earlier. It's calcium carbonate, and when you heat it, it decomposes into calcium oxide and carbon dioxide. So this guy is a solid, so is this one, and this one's a gas. And remember, you need to write their state in brackets always. Is this balanced? Fatma, is this a balanced equation?
No. Wait, S. I don't think it is.
All right. So how would you check?
We have we have two
Two,
on the reactant side, but
two of what on the reactant side? This is the reactant side. The left hand is always the reactant side.
yes. Um,
So the way we do it is we look at the number of atoms of each element on the reactant product side. So here we've got calcium. We just got one of these. And on the product side, we have one calcium. So as far as calcium is concerned, it's balanced. You've got one carbon on the reactant side and one carbon on the product
It's
side.
already balanced.
Yeah. And then you've got three oxygens on the reactant side. And then you've got one oxygen here and two here. So that's three oxygens. So it is balanced already. Okay. Now that it's balanced, again, we know that 1 mole of calcium carbonate decomposes to give 1 mole of calcium oxide and 1 mole of carbon dioxide. Now, how much does that correspond to in mass? So, the mass of calcium carbonate, we did calculate it earlier, and it's 100 grams, right? So, 40 for calcium, 12 for carbon, and 16 times 3 for oxygen, which will give you 100. Right over here, you've got 40 plus 16, and here you've got 12 plus 16 times 2, which is 32. And these give you 56, and 32 and 12 is 44. Right, and so these are the molar masses because they're all 1 mole each. So this is the ratio. So right, if we so 100 grams would give 100 grams of calcium carbonate would decompose to give 56 grams of calcium oxide, and 44 grams of carbon dioxide gas would also be produced. We can use that to calculate any, the amount of calcium oxide produced with any mass of calcium carbonate that we have. So we're being asked to calculate the amount of lime produced when 10 tons of limestone are heated. Right? 10 tons of limestone. So, how much is a ton? 1 ton is 1,000 kilos. And we know that 1 kilogram is 1,000 grams. Right? So 10 tons would be 10 million grams of calcium carbonate. Right? But okay. So what we can do is, in fact, I'll come to that later. So this is 100 grams to 56 grams and 44 grams. So I don't need to rewrite the equation. What we can do, okay, fine. Let's say if this were not 100 grams, but 100 tons. And for ton, we're just going to write T. If this were 100 tons of calcium carbonate, that would give us 56 tons of calcium oxide or lime, and 44 tons of carbon dioxide gas would be produced. Now we just need 10, right, which is 1/10 of 100. So we divide all of that by 10, and so what we get is 10 tons of calcium carbonate or limestone will give us 5.6 tons of calcium oxide and 4.4 tons of carbon dioxide gas will be produced. Did you follow that?
Yes.
Yes, Fatma?
yes.
Okay. Right. Another way you could go about doing it, if it seems easy, right, is you could just take a ratio. So, right, since it's 100 and 56 and 44, it's sort of like 1:5.6:4.4. And right, so we can use that ratio for whatever you have. So it's 10 tons, right? Disregarding the ton, it's 10 is to, in fact, no, 1 is to 0.56, my bad. So it would be 10 is to 5.6 to 5.4, or 1 is to 0.56 is to 0.44. So yeah, if that works for you. Otherwise, right, we just take it up to a higher value to make it simpler to use, and then we can bring it back down to what we actually require. All right, next up are gases. Now with gases, we are dealing with volumes. All right, so 1 mole of gas occupies 24 decimeter cube at RTP. Right? So the situation that we are being provided with is the burning of hydrogen in oxygen to produce water vapor. So hydrogen burns in oxygen, all gases, to produce water vapor, which is obviously a gas. Sophia, is this balanced?
I mean, no.
So
Wait. Yeah, it is.
it is.
I mean, we have 2 hydrogen,
Yeah.
and we have 2 hydrogen on the other side. Though we have 2 oxygen, but that side has only 1.
Yeah, so it's not balanced.
Yeah, so we gotta put 2 on the product side,
Hmm.
which gives us 4 hydrogen, right?
Hmm.
So we gotta put 2 on the reactant side for hydrogen.
Right. So now it's balanced. And again, this tells us 2 moles of hydrogen react with 1 mole of oxygen gas, where they're both diatomic, to give 2 moles of water vapor. Again, we get into the masses, or in fact, no, not the masses, but the volumes in this case, right? So they're gases. So 24 decimeter cube is the volume of 1 mole, and you've got 2 of those, right? This is just 1. So 24 decimeter cube, and again 2 moles, so that's twice of 24. And so 48 decimeter cube of hydrogen reacts with 24 decimeter cube of oxygen to give you 48 decimeter cube of water vapor, right?
Yeah.
Now the question is, calculate the volume of oxygen used and water vapor produced if 960 decimeter cube of uh, hydrogen gas is burned in oxygen, right? So 960 decimeter cube of hydrogen is burnt. What are the volumes of O2 and H2O produced?
Could you repeat the question?
The ratios we have are 2:1:2.
Yeah.
And so the question is, right? I mean, we've got 48 decimeter cube of hydrogen reacting with 24 decimeter cube of what you call it, uh, oxygen to produce 48 decimeter cube of water vapor. Now they're scaling it up. They're asking you, okay, so using 960 decimeter cube. So that's the volume. We're using 960 liters or decimeter cube of hydrogen gas. We are burning it in oxygen. How much oxygen do we need in volume, and how much water are we going to produce?
Um, we're gonna volume over. We're gonna calculate the moles of hydrogen first from the given volume. If I'm not wrong.
We don't need moles, do we? We're not being asked for moles.
Okay.
How else could we go about doing this?
Volume. You need volume, right?
Hmm.
So moles multiplied by dm cube.
Okay.
If I'm not wrong. Or am I?
So since we're talking about hydrogen over here, it's the way they've gone about doing this, right, is they just take a look at the numbers, and again, right, start small and then scale it up or scale it down. And so what they're doing is 48 times 2 is 96. Right? If you had 96 decimeter cube of hydrogen, it would be reacting with 48 decimeter cube of oxygen and giving you 96 decimeter cube of water vapor. Then you multiply this by 10, and that gives you 960 decimeter cube of uh, hydrogen, which is what you want, what you have. And you similarly scale all of these up by a factor of 10 as well. So you're getting 480 decimeter cube of oxygen. And
Question.
yeah, just a sec. Yes,
Why would you do it with 10?
because 96 times 10 is 960, which is the volume you have in the question.
Oh, okay. Okay. Got
Now,
it.
this is sort of a roundabout way, right? What if I mean, they've obviously used values that are easy to deal with. 48 times 2 is 96 and 960 and all of that. Another way you could do it, you've got, right, so a balanced equation has 48 decimeter cubes of hydrogen gas. Yes, Fatma, you're following along?
Yes.
Okay, so a balanced equation has 2 moles of hydrogen gas, which is 48 decimeter cubes by volume, and what we're being asked is 960. So what you do is, this is what you have, and this is from a balanced equation. And what you get is a factor of 20. All right, 960 is 20 times more than what you're using. And so you take this factor and you basically, I mean, that's what they've done over here, right? First multiply by 2 and then multiply by 10, which is a factor of 20. But it seems like a roundabout way of doing it, right? Doing it. You get a factor of 20. And you take that and you multiply that throughout. Because if you're using 20 times more of hydrogen gas, you are getting 20 times, you will need 20 times more of oxygen as well. And you will produce 20 times more of water vapor. Does that make sense, Sobia?
Yeah.
Right? So you take the 48 and the 24 and the other 48 and you multiply this whole thing by 20, and that will give you 960, which is what we had, which is what we're being asked, and the 480. You're getting this, and this, right? And that's H2 and O2 and H2O. Okay.
Okay.
Then we've got solutions. So in solutions, we are concerned with concentrations. So we're going to do this through two examples. And we do have time on the clock. I don't know whether we'll be able to complete this today. If not, definitely tomorrow.
I mean, yeah, it's 4:36 on your side.
Okay. So the first situation that we have is they're asking us to calculate the volume. You have 1 mole per decimeter cube of sulfuric acid. That is the concentration of sulfuric acid you have. And you are reacting it with 6 grams of magnesium. So remember reaction of metals with acids?
Okay.
I mean, do you remember reactions of metals with acids?
Oh, yeah. Yeah.
What are the products we get out of that? Let's write this out.
Yeah.
So you've got magnesium, which is a solid, and sulfuric acid, which is aqueous. And what do we get?
Just a minute. MgH2SO.
Mg what?
MgH. MgSO.
MgHSO?
No, only SO.
SO4.
Yeah.
So we're getting a salt, magnesium sulfate.
Yeah.
What else?
H.
Not just H. H2, hydrogen gas.
Yeah.
Right? Is it balanced?
Wait, let me see. No.
It's not. Fatma, do you think it's balanced?
Is on the reactant side, did you wrote 4 beside SO?
Yeah,
Yeah, okay, then it's balanced.
it's balanced, right?
Yeah.
So that is the balanced equation. And so 1, 1, 1, and 1. You got 1 mole of all of these guys. Right?
Yeah.
Now, what we need to find out is how much volume of sulfuric acid do we need to react with 6 grams of magnesium. So what do we do? What do we start off with? The first thing we're going to do is find out so we know the molar ratios of the balanced equation. We find the number of moles of magnesium. How much is 6 grams of magnesium? And so that is 6 divided by, what was the, right, 48, sorry, 24. So 6 divided by 24, which is how much?
4?
6 divided by 24.
Oh, okay. It gives us 0.25.
0.25. Right, so we are using 0.25 moles of magnesium, right? And by that, we will also be needing 0.25 moles of sulfuric acid. Now what they're asking us is the volume. So how do we convert the, so we are going to write zero, we are having 0.25 moles of sulfuric acid reacting with the same number of moles of magnesium. How do we convert this into a volume?
Mm.
Right, so volume, right, of H2SO4 sulfuric acid equals to moles of H2SO4 divided by the concentration. If you just go back to solutions, right, so concentration is number of moles over volume, right? So what we want right now is the volume. So volume would be number of moles divided by concentration,
Okay. Yeah.
right? And that's
Yeah.
what we're doing. So
Yeah.
again, it's not new. If you remember the basic formula, right, you can use them as you require. And so that gives us 0.25 moles over 1 mole per decimeter cube. And that gives you volume of sulfuric acid as 0.25 decimeter cube, right? And if you want to convert that into centimeter cube, you multiply that by 1,000, and that will give you 250 centimeter cube. So that is how much sulfuric acid you need for a complete reaction with 6 grams of magnesium.
Okay. Yeah.
Making sense,
Yeah.
Fatma?
Yes, sir.
Okay. There's another question. There's another example, and this time they're giving you the information that you have 40 centimeter cube of 0.2 mole per decimeter cube of hydrochloric acid, right? And it was used to neutralize. This is the volume and concentration of hydrochloric acid that was used to neutralize 20 centimeter cube of sodium hydroxide. Right, so this is a neutralization reaction and it's done via titration. Titration is something we left for later. Right, so now that we are almost done with the chapter of moles, we'll go back and visit titration after this. So the question is, what is the concentration of the sodium hydroxide solution used in grams per decimeter cube, not moles per decimeter cube, but grams per decimeter cube? So concentration of NaOH solution in grams per decimeter cube. So how do we start off with this?
We have to find the decimeter cube, right?
We have to find the concentration of sodium hydroxide, the sodium hydroxide solution. The first thing we need to do is write out a balanced equation. So you've got HCl aqueous and NaOH aqueous, giving me, what do we get,
Mm.
Fatma?
Sir, I don't know.
HOH.
HOH, that would be water.
Oh wait. Sorry.
No, we do get water. right? But that is obviously not our main product.
HNC. No, wait.
Salt,
NaCl
yes,
plus H2O.
yes.
Okay.
And this guy is also aqueous, and this guy is a liquid, right? Is it balanced?
Yeah.
It's balanced. And so you have a ratio of 1 to 1 and 1 is to 1, right? So they're all 1 mole each. Now, what you have been given is the volume and the concentration. So going back here, we need to find the
So
number
we
of
have
moles.
to convert the volume into
How?
dm cube.
No, no, no. What we need to find out right now is what number of moles, right? So we know that 40 centimeter cube of the hydrochloric acid of this concentration. Wait, did I just go back? Right. 40 cm cube of 0.2 moles per decimeter cube. So that's the concentration. That is the hydrochloric acid we used. So the question is, how many moles were there? Right. So how do we get the number of moles of HCl? Again, we
HCl has wait. HCl has 0.02
see
moles. No, it's zero
why
6.0.
why are you taking guesses? Here's the formula. So number of moles, if you move this around, is volume times concentration, right? So the volume and the volume needs to be in dm cube, right? So what we're going to do is divide 40 by 1000, and that is going to give us 0.04.
For HCl.
Yes, you need to convert 40 centimeter cube into dm cube because the concentration is in dm cube, and we multiply that by 0.2 mole per dm cube, and what do we get? Soviet 0.2 multiplied by 0.04,
0.008.
0.008 moles,
Yeah.
right? So that is the number of moles of hydrochloric acid that were used. And so since the ratio of the right hydrochloric acid and sodium hydroxide are the same, that means 20 centimeter cube of NaOH had 0.008 moles in it.
Yeah.
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 So right, first of all, we find out the concentration. So what was the concentration of the sodium hydroxide solution that we used? And that would be right number of moles divided by the volume. Right?
Yeah.
And so that would give us 0.008 divided by
0.02.
0.02, which will give us what?
0.4
0.4
mold.
mole per decimeter cube. This is concentration,
Yes.
right?
Yeah.
So we have 0.4 moles of sodium hydroxide per liter in that solution, right? But what they've asked us is the
Is
concentration
gram.
in grams. So how do we convert moles into grams?
Uh-huh. You multiply the molar mass of NaOH.
Exactly. Good. So what's the molar mass of NaOH?
40 approximate. Yeah, 40.
40, right? So to break that up, so the molar mass of NaOH is 23 plus 16 plus 1, which is 40 grams, right? And so you want to know how many grams is in 0.4. So you do 0.4 multiplied by 40, which will give you how many grams?
16 gram over dm cube
Right, 16 grams is what's in 0.4 moles, and so the concentration of the NaOH solution
is 0.4.
16 grams.
Okay. Yeah. Oh yeah, 16 grams. Yeah.
So that's what they're asking.
Yeah.
So what you said earlier was correct, but right, we just found the mass in a liter. So again, the formulae and the concepts that we've covered earlier, those are what are applied, right? So you just need to have them ready to use depending on the situation, whether you're dealing with gases or you're dealing with solutions or whatever it is, right? And it's not, I mean, if you keep your head about it's right, you just need to be careful step by step of what you're doing, right? And the first very important step is to write balanced equations, figure out the mole ratio of all the reactants and the products, and then whatever information you have, you know, even if you have the number of moles of any one of these guys, right? So this is 1:1 throughout, but if like we did earlier 2:1 or something, and so if you have the mole ratio of any one, then you can calculate all the others, right? So back here we had 2:1:2, right? And so for example, if that wasn't the question, but if I said that I used 18 grams of hydrogen gas, how many grams of oxygen gas would I be using?
Would you repeat that?
If I used 18, so the ratio between hydrogen, oxygen, and water is 2:1:2, right? The number of moles. If I
Yeah.
used 18 grams of oxygen, sorry, hydrogen, then, right, how many would I, what mass of oxygen would I be using?
Mm. Sir Fazma likes to answer.
Would you like to answer first?
Sir, I'm still processing.
Yes, I'm here.
All right, let me write this on a, because we're just about out of time, so the percentage yield stuff will have to wait for tomorrow. Let me write out here. 2H2 plus O2 gives 2H2O. So the mole ratio between these guys 2:1 to 2. Right? Those are the moles. What if I used 18 grams of hydrogen?
Mm.
The first thing you should do is how many moles there
We have to calculate molar mass.
are. Hmm?
We have to calculate molar mass.
Yeah, so 18 divided by 1 is 18. So
Yeah.
you're using 18 moles of hydrogen,
Yeah.
right? And so this is 18 moles. And so how many moles of oxygen would you be using there?
One mole?
Seriously?
Right.
Look at the ratios. 2:1. So you're using twice as much as of hydrogen as of oxygen. So if you're using 18 moles of hydrogen,
36.
how much?
36.
Why are you multiplying it by 2? Supposed to
So
divide.
18.
No,
Because there is one molar mass for oxygen.
9.
So we gotta do 18 multiplied by 9.
18 multiplied by 9. Sobia, what are you up to?
Sir, is it because we have 2 moles and then we have 1, so we have 18, so we're gonna have to have half of it?
Exactly.
Oh.
Exactly. Right? That is why a balanced equation and the ratios are important. Right? So I'm using 18 grams of hydrogen, which is 18 moles. Right? When 2 moles of hydrogen react with 1 mole, so you're using half the oxygen as compared to hydrogen. So when you have 18 moles of hydrogen, you will be using half of the oxygen, which is 9. Right? And obviously you're going to be getting 18 moles of water. Now, what's the mass of oxygen you're using? So 1 mole of oxygen gas is 32 grams multiplied by 9 moles, and that gives us what? 32 multiplied by 9.
288.
288 grams. Right? So interestingly, 18 grams of hydrogen need 288 grams of oxygen, which is obviously, right, much more in terms of mass. In terms of moles, it is less. Right? Why is it less in terms of moles? Because, right, the mass of oxygen is much more. It is 16 times more than hydrogen, even though the molar ratio is different. Does that make sense?
Yeah.
And how much water will you get? So 18 times, what's the, right, that's 18 grams. So that's the molar mass times 18 moles. So 18 squared. That's 324 grams of water that will be produced. So you'll get a glass of water out of this.
Yeah.
Sobia, did you follow?
Mm-hmm.
Okay. Fatma?
Yes.
Okay. So I'll stop here for today. And right, we'll continue with percentage yield and percentage purity and all of that, and hopefully the titration part as well. And we'll be done with stoichiometry, which will leave us with only chapter 14, which are experimental techniques. I wanted to have this done by the end of Feb, but we'll be going into the first week of March with this, which still isn't too bad. And then we'll be done with the syllabus, so we'll carry on and start with we'll start practicing past papers. Right. Also, tomorrow's class will be at 3 p.m. Right, Sobia?
Mm-hmm.
Right. Okay. So I'll see you guys. Well, any questions? Any questions about today?
No.
Fatma?
No.
Okay. So I'll see you guys tomorrow. Well, Sobia at least. Hopefully you too as well.
Yeah. Allah Hafiz.
Yes, sir. Office.
Allah Hafiz.